remind you that the midterm for the course is, right? So on the 25th, in class, it's open textbook, and you're allowed to use your class notes. And there's a homework due tomorrow, and I spoke to the TA, and I expected a lot of you had questions about some of it on the problem. So it was not a straightforward homework, and it wasn't meant to be a straightforward homework. So we were expected to do a little extra work beyond what we discussed in class. And the fact, if you weren't able to do it in your first try, that doesn't mean anything. Don't get discouraged. We are here to teach you some of the things. So if you have difficulty, talk to the TA, talk to me after class today. I'll be available till 12:30. And we learn how to do those problems.
Would you be willing to go over any of the class?
Sorry?
Would you be willing to go over any of the class?
Actually, so the best way to learn from these homework problems, excuse me. Hello? I believe so. Yes, of course. Yeah. So the best way to learn would be for you to make an honest attempt. And even if you don't succeed in solving the problem, it doesn't matter. Then when you look at the solutions that are posted, that'll make a lot more sense. And you will learn, where you went wrong or where you hit a wall, and why you weren't able to proceed. As you know, there is some credit for the homework. I think about 25% for homework and it's about participation. But actually, that, historically speaking, does not make such a big difference to your final grade. So it's basically your performance in the exam that counts much more than the homework. So therefore, the role of the homework is to make sure that you learn the material well. And just as the role of the lectures is to make sure that you learn the material well. So if at any point you don't feel comfortable doing the homework, and you're not able to do some problems successfully, then it just means that there is a little gap in your understanding that can be fixed by learning how to do it. So, to answer your question, I probably won't discuss anything in class unless there's a real need for it. So, for example, if I find that 95% of the class is not getting something, then I'll probably come back and do it. But otherwise, I think the solution to the homework will be fairly complete. And if you read the solutions and you still don't know, you still have a question as to how it was arrived at, then you're welcome to come back and do it again. Okay. So what I want to do today is to wrap up duality and also have sensitivity analysis. So to wrap up duality, what I have to show you is proof of the strong duality theorem. And we've been working towards this proof for the last 2 lectures. So let me remind you what the theorem itself says, then let me illustrate how one might use the proof. So the strong duality theorem says the following. You give me any linear programming problem which has a finite optimal solution. Then the dual problem also has an optimal solution to the same objective value. So notice that it asserts 2 things. First, it says that the dual problem is feasible and has an optimal solution. And secondly, it says that there is no gap between the 2 solutions. So in our lectures, we use the primal problem as a maximization problem. And we motivated the dual problem by saying we want to compute upper bounds on the objective value of the maximization problem. And we already know that any feasible dual solution is an upper bound on the value of this problem. So therefore, we know that that if this problem is feasible, and if the dual problem is feasible, then any dual feasible solution has value at least as much as final feasible solution. So in particular, the dual optimal solution has at least as much value as the final optimal solution. Final is a maximization and the dual is simplification. This was the weak duality theorem, and the proof of this was just one line, analyzing an expression that sort of cropped up in problem 4 of your homework. The proof of strong duality theorem is slightly more involved, but not much more so, once you understand that the simplex method, or the optimal dictionary, encodes the dual solution of that. So let me work with that particular problem. It's a primary. We formulated the dual in class. And I want to show you how one can prove that whatever is in the last row is a feasible dual solution. Or you can get a feasible dual solution from whatever is in the last row. Okay, so the problem in red is the primal problem. I'm not going to write down the dual explicitly, but we probably need to do so in a little bit. But let's actually understand what the last row says. So the last row says that you give me any feasible solution to the primal problem. It's going to satisfy this equation. In other words, any feasible solution to the primal problem is going to satisfy z equals 55 minus s3 minus s3. But what is z? Z is just our original objective value, original objective function. So that equation can be written as follows. Written as 2x1 so 2x1 plus 3x2, which is 3, is 55 minus, so I want to do this a little more detailed. So all that equation says is 55 minus s2 minus s3. Let me write it out explicitly again. This is going to be 55 minus 0 x1 minus 0 x2 minus 0 s1 minus s2 minus s3. That's what the last row says. So take any feasible solution to the primal problem. It satisfies this equation. And this is the reason for saying that the solution that you currently have, which sets s2 and s3 to 0, and x1, x2, s1 to whatever is given by the first three equations, this is the reason why that's an optimal solution. Because you know that any feasible solution to the problem has this quantity equals 55 minus all of this. And so if you can set these two things to 0, you get a solution value 55, and that's possible. Okay, so we've gone through this reasoning at least half a dozen times, but it's worth repeating. Now, what I want to do now is explicitly write down what S1, S2, and S3 are. Okay. Now my claim is that these coefficients are really my y1 stars, right? So I claim, so my claim is that the optimal dual solution is y1 star equals 0, y2 star equals 1, y3 star equals 1. We want to show that this is optimal for the dual. So this is what we suspect. In fact, we know that this is an optimal solution for the dual because we solved the dual explicitly. But we want to infer the optimality of this solution for the dual problem just by looking at this equation. Okay? So I can rewrite this as 5 minus 0x1 minus 0x2 minus y1 star x1 minus y2 star 2 minus y3 star. Yes. Oh. Okay. Now, what is S1? What are S1, S2, and S3? They are the slack variables, right? Now, we know that S1 is expressible in terms of X1 and X2. So we know in particular that S1 is 5 plus X1 minus X2. That's the definition of S1. Similarly, S2 is 35 minus X1 minus 3X2. And S3 is 20 minus X1. So these are the definition of S1, S2, and S3. Right? This is what we mean when we say X1 minus X1 plus X2 plus S1 equals 5. That's our first equation. So I'm going to use these values here over here. So what is that? So I get 55 minus 0, 1, 0, 2, y1 star times. So I'm going to use 5 plus x1 minus x2. Okay? Minus y2 star times 35 minus x1 minus 3x2 minus y3 star times. So it's not important that you write down all of this because I'm going to put this in the lecture notes anyway. So it's more important that you follow what's happening here. So what I've done is I've just taken the last equation and expressed everything in terms of the x variables. Okay? And we suspected that the coefficients of the slacks in the last row give us the dual solution. So I have just indicated that explicitly by putting y1 star, y2 star, and y3 star instead of 0, 1, and 1. Okay? So these are the only two changes that we've made. And notice that any feasible solution to the primal problem satisfies this equation. That's the key thing. Okay? Any questions about this transformation? Okay. Now, let's actually simplify this. So we get this is 55 minus 5 y1 star minus 35 y2 star minus 20. So this is going to be the constant term. Okay? So I just pulled out the constant term. And then I have plus x1 times, what is the coefficient of x1? So it's going to be negative y1 star, positive y2 star, and positive y3 star. Okay? And what about the coefficient of x2? y1 star, 3 y2 star. Okay. So after I do the obvious simplifications, I get 2x1 plus 3x2 equals this quantity. So I have an expression which is satisfied by every feasible primal solution. Okay? And we assume that there are feasible solutions to the primal problem, because we assume that there is an optimal solution to the primal problem that I have achieved. So every feasible solution to the primal problem satisfies this equation. Okay? So what must be true? The coefficients have to match. So in other words, you must have 2 equals negative y1 star plus y2 star plus y3 star. Okay. And similarly, 3 equals y1 star plus 3 y2 star. Not only that, what else must you have? This quantity has to be 0, right? Yeah, 55 equals 5 y1 star, 35 y2 star, 20. So, once again, this is something that's very, very simple, but I think it's understanding all of the steps will suggest a general proof that I want to outline next. So we took the last equation, got rid of all the flat variables, expressed everything in terms of the x variables, the original variables of the problem. And instead of the coefficients of the flat variables, we just use y I star. And so this is just because we suspected that those coefficients actually give you an optimal dual solution. So I'm just calling them something, in this case y1 star, y2 star, and y3 star. And I gave out a list of conditions that have to be satisfied because every primal feasible solution satisfies these equations. So what I do know is the coefficients of the last row, whatever those quantities may be, which I'm calling y1 star, y2 star, and y3 star, they satisfy all of these. So whatever coefficients I have for the slack in the last row satisfies this equation, and this equation. Okay, any questions about this? Okay. Now, let's write down the dual of this problem. Actually, we don't have to write it down. We can just get it from here. So the dual of this problem is going to be minimize 5y1 plus 35y2 plus 20y3. So maximize the negative of that. And you have a whole bunch of constraints. Okay? So I claim that this proves that you have an optimal dual solution. Why is that? Well, another way of writing down that dual problem is, let me actually write it here so that it's easy to see. So this is minimize 5y1 plus 20y2, sorry, 35y2 plus 20y3, subject to minus y1 plus y2 plus y3 being at least 2, and y1 plus 3y2 being at least 3, y1, y2, y3 non-negative. Sorry? Oh. It found some updates doing that, so I'm going to restart it soon anyway. Okay, so here is the dual problem. Okay, and here are the conditions I got from looking at the last row of the primal dictionary. So I know that the coefficients of the slack in the last row satisfy this, this, and this. Okay? So which means that the coefficients are feasible for the dual. Okay? Why are they feasible for the dual? Well, this quantity is the coefficient satisfied. If I take y1 to be y1 star, y2 to be y2 star, and so on, I get this quantity equals 2. So it satisfies this constraint and satisfies this constraint. Why are they non-negative? They are non-negative because you looked at the optimal dictionary for the primal problem. And so the coefficients here, you're guaranteed that they'll be, these coefficients are guaranteed to be non-positive. And we were looking at the negatives of those, right? We took y1 star to be 0, y2 star to be 1, not minus 1. So because we look at the negatives of these coefficients, and these coefficients are guaranteed to be non-positive, the negatives of those are guaranteed to be non-negative. So you found non-negative values for the y's satisfying both of these constraints. Why is this an optimal dual solution? So far what we've shown is that if you look at the last row of the primal dictionary, take the negatives of the coefficients associated with the slack, you get a solution that's dual feasible. Okay. So that's what these two things show you. How do you know that that solution is actually optimal for the dual? This CF condition. Okay, so something simpler tells you that. This equation tells you that what you found is optimal for the dual. And why? This is, if you look at it, the objective function of the dual. Okay? And what I'm just showing you is a solution whose value is 55. Now we know that any feasible solution to the dual problem has value at least 55 because every feasible solution to the dual problem is an upper bound on the primal objective value. And we know that the optimal primal objective is 55. Therefore, every dual feasible solution has value at least 55. Here's one with value exactly 55. Therefore, this is optimal. Yes? I'm sorry? How do we know that it's at least 55? Well, 55 was the objective value of the primal problem. Right? So we pulled this out of the primal dictionary. Therefore, by weak duality, any dual feasible solution has value at least 55. So this is how the proof of strong duality can be done. I showed it to you on an example, and I'm going to show it to you in terms of symbols in a little bit. But this is the general idea, that you take any primal problem. Remember, we are only looking at symmetric primal dual forms. So primal is maximized C transpose X, AX less than equal to B, X non-negative. You take such a primal problem, you will convert it to standard form and solve it using the simplex method. Look at the final dictionary you get. Look at the coefficients of the slats. Some of them will be 0. If the slats are basic, then the coefficients will be 0. If it is non-basic, then you may have a non-zero coefficient. So look at the negatives of the coefficients of the slats, and that is going to give you a dual optimal solution. The fact that it's optimal for the dual problem is going to follow from looking at something like this, and the fact that it's feasible for the dual problem is going to follow by looking at these things. Okay, that's exactly what we did on this example. Okay. So this is a constructive argument based on an algorithm. We know one way of solving the primal problem, and we know some of its properties. We made use of it in proving a theorem. So you can actually do this without you can prove strong duality possibly without exhibiting a dual solution. But what we did is not just proving that the result holds, we also figured out a way to actually find such a solution. So this satisfies all of the conditions of the theorem. It says whenever you have a primal problem that attains an optimal solution, we know by the correctness of the simplex method that you end up with an optimal dictionary whose last row looks like this. Then take the negatives of the slats of that last row. That is an optimal dual solution. So in particular, there's a dual optimal solution whose value is the same as the primal. Now, the proof for the general case is exactly the same as this. So I'm going to show that to you in a moment. But if you have this example in mind, you will see the correspondence. Any questions about this argument? Okay. So let me do so I'm going to erase this part, one on top. Yes.
I'm not even sure if I'm on to anything valid here, but I remember in class ago that the function usually was we have conditions that the slack variables would be 0, and then in this case you're kind of assuming that the coefficients match those slack variables, meaning that they're not 0 in this case. Why is this
No. Okay. Let me back up a little bit. So the TS condition says that the product of, if you have an optimal solution, the product of a regular variable and the slack of the constraint for which it is the dual, the product is 0. So either xi is 0 or the slack associated with the constraint for which xi is a dual variable. So that we call wi. That is 0. So in terms of these things here, what that would say is either y1 is 0 or s1 is 0. Either y2 is 0 or s2 is 0, and so on. So here, all I'm doing is I'm just matching, so I'm exploiting the fact that this equation should be valid for every feasible primal solution. So if some equation has to be valid, regardless of the values of x1 and x2, the coefficients have to match. And So this is sort of knowing. So in other words, we just by doing some examples, we suspect that the coefficients of the slacks in the last row of the primal dictionary give us an optimal dual solution. And so we want to prove that because we know the answer. We are writing down a proof that looks like this. I don't know if that answered your question, but yes.
In the class, we just discussed those kind of like dictionary welcome stuff here, and like for any kind of random like dictionary, can we just the first step is throw those things through like the matrix compose into like a view or whatever. Like before we doing that, is there any kind of circuit or whatever? It should be in the standard form or somewhat.
Okay, so whenever we write down the dictionary, we assume the problem is in standard form. In other words, we write dictionaries only for standard form problems.
Okay, I could be wrong in using that term. I'm just saying like for any kind of random like linear programming thing.
Mm-hmm.
Can you just like the first step like I don't care what those values are, whether feasible or negative, I don't care. I just like do the latest compose and throw them into a do. Can we do that?
I'm afraid I don't quite get that.
This is
so I give you let's say I give you an arbitrary linear programming problem.
Yeah.
Then is your question how do you solve? How do you get started in solving it?
So yeah, I can get started solving it, but I'm just like wondering like whether before we do anything else, can we just like convert it into linear program?
So you can. I mean, so there should be a reason for computing the duals, right?
Yeah.
So the question is, so I give you a linear programming problem, and if I ask you to find the dual, then then you do it. You can do it any number of ways. You can convert that problem into a form that you like, then compute the dual. You can compute the dual for any arbitrary linear program using the rules that are given in your textbook on page 121 something, where you just see that if you have a maximization problem with less than equal to constraints, then the corresponding dual variable must be non-negative. There are rules of this sort. So there are many ways of finding the dual, and any of these ways will lead you to the right dual. They're all equivalent. And one of the homework problems asks you to show that there.
Yeah, and then the problem after that, like two different answers from two different duals.
Okay, so
I mean, each of these duals they match the original final. So there must be some calculation wrong, or my theory was wrong.
Right. So then so we can discuss the homework problem after the lecture. But the general answer to your question is you write dictionaries only with standard form problems. If you're given a problem that's not in standard form, you convert it to standard form before solving it for the purposes of this course. In practice, you can do any number of things that we won't discuss. But the nice thing about working with a standard form is that it's enough to design an algorithm that works for standard form. I don't have to tell you, if you start with an LT that has a different structure, I don't have to design another algorithm for it. I know that I can always convert it to standard form, apply the method I know. So always you convert it to standard form and do the dictionary. Now, in the case of duality, I assume that the problems have a certain form, so that the primal and dual cannot be symmetric, so that we can invoke a lot of these arguments. That's also without loss of generality, because any linear programming problem can be converted to that form. It may not be the best thing to do in terms of computation, but in terms of understanding, it's easy. So you just have to remember one set of problems, one set of rules to compute the dual and so on. And I also have to warn you that if you take a problem in standard form, so I give you a problem with equality constraints only, then this approach does not tell you how you would find a dual solution. Well, it tells you, but so remember, this argument says, look at the coefficients of the slack variables in the last row. Take the negative of that, that gives you a dual solution. Now suppose I give you a problem that has for which the slack variables are not needed at all. So I give you a problem with 5 variables and 3 equations. It's already in standard form. Then, what I've shown you does not tell you how to find a dual solution. Right? Does everyone see that? So I've showed you how you can find a dual solution only for problems of the form maximize P transpose X, AX less than or equal to B, X non-negative. So that for every constraint you add a slack variable, and the negative of the coefficient of that slack variable in the last row, the optimal primal dictionary, is going to give you the dual solution. If I give you a problem directly in standard form, how do you find the dual solution? That's something that I'm going to leave you to think about. It's not difficult, and as you would suspect, it's still buried in the last row. You have to do a little extra work to recover the dual solution. You will see. Okay, so let me quickly show you the general proof, okay, which will follow exactly the same argument that we did on this example. And you should be able to associate every step, in fact. So let me get rid of, actually, let me get rid of this. Okay. So again, I'm going to assume that my problem is maximize C transpose X. And the dual for this problem is minimize P Y, Y A is a P C, Y non-negative. So the last row of this optimal primal dictionary is going to look like Z equals Z star plus So this is how the last row is going to look, right? Let me use a negative sign like I did in my argument. So it's going to be Z star minus Cj bar Xj minus Di bar Fi. Now what we know is that Cj bar is non-negative, Di bar is non-negative for all. Okay. So this is what we know. Now, we also know that some of these coefficients will be 0. So which of these Cj bars and Di bars will be 0? If Xj is basic, then Cj bar is going to be 0, because we know that none of the basic variables is going to appear on the right-hand side of the last row. But it doesn't matter. You just have non-negativity for this coefficient, so you will put a 0 there. Okay. So this is the same as V star minus Cj bar xj minus Bi bar, and Si is just going to be Vj minus Vi. So it's going to be the difference between the amount of resource of pi you have, which is Bi, and what you consume of that resource, which is Aij xj summed over all j. So j goes from 1 to n. Okay? So this is going to be Z star minus that's the constant term. And then you're going to have summation I going, j going from 1 to n. The coefficient of xj is going to be minus Cj bar. That's from here, and the coefficient of xj is going to be Bi bar Aij summed over all r. Okay? So you just took this equation, expressed everything in terms of xj, and this must be true for all xj. This is true. So remember that the left-hand side is just v, which is summation Cj xj. So you must have this equation satisfied for every possible value of x1 through xn. Okay? So this happens only if, so for this to happen, you must have, just like we match the coefficients, you have to match all the coefficients. So this implies you have Cj equals minus Cj bar plus summation I equals 1 to n Bi bar Aij. So the coefficient of xj must match. Moreover, summation Bi bar Bi equals V star. Okay?
I don't see how you get
So this is just V, right? V is just Cj. This is the definition of the objective value of the primals. So we said the primal objective should equal all of this, which we simplified to this. But if you look at what the primal objective is, it's just this quantity. So for this equation to be satisfied, for every value of x1 through xn, you must have the coefficient of xj on the left-hand side equal to the coefficient of xj on the right-hand side. Moreover, you must have this term to be 0. Exactly the same reasoning we did in the example, we are doing it here. So what does this mean? So this, when we simplify, we get summation Bi bar Aij, I going from 1 to n, equals Cj plus Cj bar. Which we know has to be bigger than Cj. Why do we know this? Because we know that Cj bars are all non-negative. So if it is equal to Cj plus a non-negative quantity, it's a Cj. We also know that di bar di equals Z star, and we know that di bars are non-negative. So these two things imply di bars are dual feasible, and this, so these two in conjunction with this, so if I add this, I get dual optimal. So that is the proof. Yes. Sorry? Let's see. So, do you want me to go through this again, one more time? Okay. So, we look at the last row of the primal dictionary, which looks like Z equals Z star minus this quantity minus this quantity. Okay? Now, because it's an optimal dictionary, I know that the coefficients of every variable here is non-positive, which means Cj bars have to be greater than or equal to 0, and Di bars have to be greater than or equal to 0. Not only that, I also know, although we don't make use of this, that if any variable is basic, then its coefficient is 0, the last equation. Okay? So I just simplify this by observing that the slack is just the difference between Bi and this quantity. This is the definition of the slack. And I simplify that, and I get this expression. So the left-hand side is just the primal objective function. The right-hand side is this quantity plus this quantity. This is just rewriting this in a slightly different way. Now, if this equation has to be satisfied for every possible value of x1 to xn, then it better be the case that the coefficient of xj on this side matches the coefficient of xj on this side. And that this quantity here, which is a constant, be 0. So that's what these two conditions mean. But once I look at the coefficient of xj, I get this, if I match them. That implies that this must be true. This quantity has to be at least Cj because the Cj bars are non-negative. So what I find is, I have found these Di bars satisfying all the constraints of the dual problem. These are exactly the constraints of the dual problem. If you write down the dual of the primal, write down the dual of the given linear program, you will get these as your constraints. So these two put together say that the D bar that you found is actually feasible for the dual, and you found a dual feasible solution whose objective value is the same as your primal optimal objective value. Therefore, the dual feasible solution must be dual optimal. Okay? Yes?
Going back to our problem, what is exactly D if there is, do the problem work?
So your question is with respect to this example, and what are the C bars and the D bars?
Yeah.
Right? Okay. So to find the C bars and the D bars, you go to the optimal primal dictionary, which is that one. So if you look at this red dictionary over here, it tells you that D1 bar is 0, D2 bar is 1, D3 bar is 1. Moreover, it says P1 bar and P2 bar are 0. Okay, x1 and x2 don't appear. So I just called the coefficient of the x variables in the last row as P bar and coefficient of the slack in the last row as D bar. Any other questions about this proof?
Sorry, can you say it again?
So in terms of this example, the C bars are both 0, and the D bars are 0, 1, and 1. So just using the definition. So what we just proved is strong duality. You're asking if the coefficients have a name?
No. We got to prove strong duality. Didn't we prove the example? We talked about this now.
So we proved strong duality in the example. And this proves strong duality for general linear programming, right? You take any linear programming problem. If this has a primal optimal solution, look at the dictionary. Look at the last equation in the dictionary. And if you look at the negatives of the coefficients of the slack, they are dual feasible and dual optimal. That is strong duality. Any other questions? So it's a very simple proof after we did enough work to understand all the details. Okay. If you understand this proof, okay, then you should be able to figure out how to find an optimal dual solution if I give you a problem in standard form directly. So I'm going to leave you to think about that question. So if I give you a problem in standard form directly, so there are no slacks associated with the primal problem, and I want you to find a dual solution from the last row. You just think about or understand this argument, you will actually see what you should do. Okay? So I'm just going to leave that to you as a little exercise for which you will see a solution definitely before we learn.
Do you mean we don't have to go through all the steps and like just look at the standard form directly? Without even go through the like?
No. So the point is, by looking at this dictionary, I can say that the dual optimal solution is y1 star is 0, y2 star is 1, y3 star is 1. Suppose I give you an arbitrary problem that's not in this form, but actually that looks like this. Then, what would your dual optimal solution be? Can you infer it just by looking at the last row of the primal dictionary? The answer is yes. We have to do a minor computation, but you can test, and that's an exercise that I need you to consider. Okay, so this is going to wrap up duality. So what we did was we started with, so far basically we've done primal simplex method, dual simplex method. We understand what the dual problem is, what its relationship is with this primal problem. And we proved a few results about the primal dual pair of problems. So we saw weak duality, we just proved strong duality. We showed the equivalence of strong duality in complementary flatness conditions. And so we have a general understanding of this pair of problems. Now what I want to do is what's called sensitivity analysis. And what that is a study of how your optimal solution changes with small changes in problem data. So if you modify certain aspects of the problem in some way, does your optimal solution change? If it does change, how does it change? Does it go up, go down? What rate does it go up at, and so on. So that's going to be the topic for the remaining 15 minutes, and hopefully we'll be done with it on Tuesday. So here is so let's say that you start with that problem. Okay. And here is the optimal dictionary associated with that problem. The kinds of questions we'd like to answer are the following. Now, C2 was 30 in that problem. Okay? That C2 is the objective function coefficient of x2. So if you go back to this, okay, and instead of 30, suppose I change it in some way. Okay. Suppose we change it to, let's say, 45. Would the optimal solution change? It's actually quite interesting here because we're looking at x2, and x2 happens to be non-basic. Okay? You can see that x2 is actually 0 in the current optimal solution. So one way to think about it is the following. So you're given this linear program, and this linear program, x1 is making a certain product, x2 is making another product, and x3 is making yet another product. So you're making 3 different products, or you could make 3 different products. You have these resource constraints. And right now, the profit from x2 is 30. And it somehow is not sufficient for you to produce x2, because you're better off using the resources elsewhere. Even for producing a product with lower profit, because presumably consumes fewer resources. So the question is, what happens if I modify the value of x2's coefficient in the objective function? So I could change it. So I'm going to keep everything as fixed, and this is how we do sensitivity analysis. We vary only one thing at a time. But suppose I change that to 27. Is that going to change anything? Yes? No? No? Why? Okay, so it's just common sense, right? At a profit of $30 per unit, we didn't want to produce it. So if you lower the profit, there's no incentive to change anything. And of course, nothing else changes, right? So if I lower that 30 by any amount, the same solution is going to remain optimal, because feasibility is unaffected and optimality is clear. What's going to happen if I increase it to 32? We don't know yet, right? So presumably if I increase it to 1 million, we will produce. Right? So it's not that you will never produce. But certainly if I increase it a little bit, you may or may not produce. It's not clear. Okay? Okay, so how do we answer that question? How do we figure out what values are worth producing and which ones are not? Now notice that this coefficient here is -5. Okay? Coefficient of x2 in the last row. So what is it saying? What does that -5 mean?
Okay.
Very good. So if we increase x2 by 1 unit, we decrease our objective function by 5. So therefore, if I give you, instead of $30, I give you $32 producing x2, are you going to produce? No, because if you produce some positive amount, your profit is going to go up by $2, but it's going to go down by $5. So your net change is $3, and so it's not going to be worth.
So we will let the 32 change the value of the coefficient.
Okay, so very good. So that would be a correct argument if one can argue that modifying the cost coefficient to 32 only changes this to minus 3, okay, and does not affect anything else. Does everyone see that? If we can argue that changing the objective coefficient of x2 changes only this entry and nothing else, and changes this entry by exactly the amount by which you increase C2, then that argument is the correct argument. So what happens if we change something? Well, for that it's useful to look at what the optimal dictionary looks like in terms of matrices, and which parts get affected and which parts don't. Okay? So we saw, for instance, at the end of the previous lecture, that this is how the optimal dictionary looks like. So you have a basis matrix B, and the first rows of your dictionary are xb equals that quantity. So B is the basis matrix, N is the columns of the non-basic variables, and your last row looks like this. Okay. If you change C2, remember x2 is non-basic, what are the quantities that change? Does capital B change? No, because capital B is just the columns associated with basic variables of the constraint matrix. Constraint matrix stays the same, so capital B does not change. What about little b? No. What about the N matrix? No. So B doesn't change, N doesn't change, little b doesn't change. What about CB, the vectors of cost coefficients of the basic variables? That does not change either, because that's the vector of cost coefficients of the basic variables. And we are thinking about modifying a non-basic variable, coefficient of a non-basic variable. So nothing changes except Cn. And even in Cn, nothing changes except except C2. And notice that C2 is going to play a role only with respect to x2. So nothing changes except this little term here. One component of this vector changes, and the only component that changes affects only x2, nothing else. So therefore, if I increase this by 2, the coefficient is going to decrease by exactly 2. Okay? And so a longish argument for that is the following. So useful thing to remember is how you find the B matrix and the B inverse matrix from an optimal dictionary. Okay? So how do you find the B matrix from the dictionary? Well, you can't find the B matrix from the dictionary. You need to know what the, well, you could, but it's easier to find it from the problem itself. Okay? So the B matrix is the columns associated with the basic variables. So the columns of the A matrix associated with the basic variables. So you go back in here, the basic variables are S1, X3, and X1. So the S1 column is going to be the first column of your B matrix. So that's 1, 0, 0. The X3 column, which is 1, 1.5, and 0.5, is going to be the second column. And the X1 column is going to be the third column. So that's what you see here. So that's the B matrix, yes.
So do you only take the B matrix for when you have I think, I don't understand why it's necessarily S1, X3, and whatever other variable in the base.
Okay. So it is, the B matrix is associated with this dictionary.
Okay,
So for this particular dictionary, the basis matrix is whatever I put down there. If you change the dictionary, you're changing the basis, and so you go to a different basis matrix. So this is an optimal basis. It's an optimal basis matrix. To get B inverse, of course, you can get it from inverting the B matrix, right? But actually, you can also read it from the tableau. The way you read it is you look at the coefficients of the slats in your current dictionary. So, for instance, in your current dictionary, the coefficient of S1 is 1, 0, 0. So that's the first column of your B inverse. The coefficients associated with S2 are 2, 2, and minus 1/2. Okay? So I say they are 2, 2, and minus 1/2 because I want to look at them as equations. So if you look at the tableau, it's just the column in the tableau. If you want to look at the dictionary, it's going to be the negative of the column or the column itself, depending on whether it's basic or non-basic. So if I look at the coefficients of S1 in my first three rows, the coefficients of S2 and the coefficients of S3, those will be the columns of my basis matrix. So one can actually prove this. We are not going to bother. We'll just use this as an observation. So this gives you B inverse. Okay? So you can actually, just the B inverse and knowing what the basic and non-basic variables are, you can write down the entire dictionary, which is what this representation showed you. Right? So if you know what the basic variables are and you know B inverse, then you can write down the dictionary. You don't need to do any other computation. So in particular, if I just tell you what the optimal basis matrix is, you can recover the optimal dictionary without using any method. Okay, so here's what we were trying to do. If you change the objective function coefficient, it is 30 and you increase it to 30 plus delta, the kinds of questions we'd like to ask are, how high can delta be before nothing changes? That's the range in which you can vary delta. And what happens if you change delta beyond the range? I mean, if you change C2 beyond the range, what happens? These are the two questions that we'd like to answer. And we want to do this for every other change, right? So we want to look at changing the coefficient of a basic variable, changing the right-hand side, changing coefficients of the constraint matrix, and so on. So the way we are going to go about this is to use one example. The example that we discuss is the one that I just outlined. And we want to understand the entire set of computations that one can do with it with respect to that single example. Okay. So if you change the coefficient of a non-basic variable, you just observe that only the coefficient of x2 in the last row changes. Nothing else is affected. So all you have to do is to compute the coefficient of x2 in the last row and see how that changes as delta changes. So here I just wrote down what that is. The CBB inverse is that 0, 10, 10. You can actually check that. A2 is the column of x2 in the A matrix, and the coefficient of x2 in the last row is just going to be this quantity, or the negative of this quantity. So this tells you that as you vary the coefficient of x2 in the objective function by delta, this is how the last row is going to get affected. This is the only entry in the matrix that's going to get affected. So this should convince you that the range in which you can vary P2 is you can increase it by up to 5 and decrease it by any amount you like. And as long as your changes are in that range, the same solution remains optimal. The same basis remains optimal. And here, the same solution remains optimal. Now, what happens if you increase it beyond the range? If I take delta to be 20, so instead of 30, I'm increasing it by 20. So I'm making it 50 instead of 30. Then, of course, nothing else is going to change. This is going to become 15. So instead of -5, you're going to have positive 15. So what must you do? Yes.
Another iteration.
You have to do another iteration. And what method would you use? The primal simplex method, right? So you have something that in which the feasible solution is still feasible, optimality conditions are not satisfied, so you use the primal simplex method. So that's the first simple sensitivity analysis that we do. Let me do. Well, actually, I think I should just stop. So first part of next Tuesday's lecture, we are going to discuss changes in the other changes that we talked about. Changing the coefficient of a basic variable, changing right-hand side, and changing the increasing the frequency. So I know that the notes for the previous lecture have not been posted because I wanted to do this proof. So the notes for Tuesday's and Thursday's lectures together will be posted late this evening. I'll send an email out. The solutions to the previous homework are posted in coursework along with the homework themselves. Homework 3 solutions will be posted. Homework 1 and 2 solutions are already posted. Homework 3 I believe is created as well.